Welcome back to Deep Learning for NLP. My name is Ivan Habernal. In this lecture, we'll be talking about transformer architectures and BERT, which is an interesting topic because it's mainstream nowadays, but it didn't exist 3 years back. So let's jump into that right away. So why should we be talking about BERT, and why no NLP lecture today would be incomplete without BERT? It's because BERT is a game changer. So when we talk about BERT, we mean this paper from Jacob Devlin and his colleagues from Google AI language. And it's a abbreviation of bidirectional transformers. Yes, it's all BERT. Actually, BERT is also a puppet from the Sesame stream. So sometimes you see, funny toys and puppets around these sort of research, but we take a different approach. Why BERT is important and why is it such a game changer? So not only it won the Best Paper Award at the North American conference of ACL 2 years ago, but it actually changed a lot in a way how we perceive and solve various NLP tasks. And it immediately gave state-of-the-art results for many tasks at once, basically. And it's directly applicable to different, to various domains and to different languages as well, as we will see. As I said, there's many ways how to teach BERT, and some of them could take some funny way of teaching. For example, taking costumes and pretending you're one of these animals from the Sesame Street. We're not going to do that today, but I guess this could be fun to watch. We'll take a different approach. We'll take an approach like in a way that we'll discover slowly from the beginning the roadmap towards BERT, and with the aim, like at the end, you will ask yourself, well, I could have invented it by myself. So little by little. And we'll start with a short recap of NLP tasks, because they will be tackled by the BERT architecture. So there are single sentence tasks, as we've seen before. For example, part of speech tagging, or, well, this is not in the paper, but for example, name data recognition. So we had it in the first or second lecture already. And here's an example of name data recognition. So it's a tagging task where we tag each token or sequence of tokens and label them as person or organization or location and so on. So this is considered as a sort of low-level task. And as we saw in the sixth lecture on convolutional neural networks, another sentence-based task or short document-based task is a sentiment. In this case, this is a sentiment of a sentence, and it comes from the sentiment tree bank from Richard Socher from Stanford NLP group from, I guess, 2013, 2014. And the goal here is to determine the sentiment of the sentence. This sentence is represented as a tree, so there is some composition of the sentiment, but the goal is to predict overall sentiment of the sentence, as we saw in the convolutional neural networks lecture. However, it doesn't stop at the sentence. So there is a very popular NLP task called natural language inference, NLI, with a very famous corpus now called SNLI. So it's Stanford Natural Language Inference Corpus. And the task goes as follows. So having a text, for example, a soccer game with multiple males playing, whether, if you know this sentence, whether you can, whether the hypothesis here holds or not, whether this entails the hypothesis. So for example, if you know a soccer game with multiple males playing entails some men are playing a sport, which is true in this case, so it's labeled as an entailment. There could be a contradiction like here. So there is a description of a scene. A man inspects the uniform of a figure in some East Asian country, whatever it means, and the hypothesis text is the man is sleeping, which is definitely not entailing, and then therefore it's contradiction. So this is another class in this task, and of course there is a third class called neutral, when these two sentences have nothing in common. And here's the last example of a NLP task, which I don't show a detail of that, but it's quite self-explaining. It's question answering, where there's a question in a natural language, and there are some locations of its answer or answers linked to Wikipedia articles. So the goal is to determine the markers in the Wikipedia articles given the question. So it's answering a question basically by finding where the answer is. And you might be wondering, why are these tasks hard? I mean, they are hard, but why explicitly are these hard? The point is, some methods can sort of exploit some artifacts in the data. So for example, in the Stanford natural language inference task, some surface features can be sort of leaking the true answer. So if a system is catching on these surface features, it can find the answer without actually understanding the meaning of this entitlement. So there's one example of a paper exploring this from the group of Noam Smith and Sam Bowman, the authors of SNLI, and other co-authors from NUCL 2018. So this is interesting. So what we really need to know in order to solve these tasks, and this is truly understanding the meaning of words, so some semantic information. Then we need to understand the relations between words, or their compositional meaning, or their relations of the meanings of words. Some syntax, for example, negations or quantifiers, very important features. And it goes on and on, and you have to perform some reasoning about the world. For example, for the natural language inference task, the system, in order to be able to solve it, has to understand something about the world. So as I said, we're following a roadmap before coming to actual BERT, and the first was to understand what are various NLP tasks that eventually the BERT model will be dealing with. Since this is a NLP deep learning for NLP lecture, there is some deep learning prerequisites, but as you'll see, this is everything we covered already in the previous lectures. So what we know is what we need to know, and what we know to solve these tasks. So we have this hammer of the deep learning. So we know layers, activations, softmax function, and we know convolutions. We know what we have to learn, so matrices and biases. We know loss functions already, so for example, cross entropy for classification. We know how to train them using backpropagation and SGD or Adam and so on. We also talk quite a lot about word embeddings and their different flavors. And we tackled also like multilingual word embeddings or syntax-based embeddings and so on. So this is something which we use for dense semantic representation. So this is just a short recap that, well, these are the rudimentary things that we need to know in order to understand BERT, but these are rudimentary things in order to understand anything in deep learning for NLP. So that covers neural networks that are capable of learn nonlinear dependencies, and they learn some features inherently in their representations. And also we have these embeddings. So let's move on. And we move on to neural machine translation. And you might be wondering, like, what does neural machine translation have to do with the BERT model, which is just for classification or these tasks we're talking about? And the point is, BERT actually builds upon techniques from machine translation quite a lot. And what is machine translation? So it's yet another popular task in NLP, and there's many quite large-scale parallel corpora available, and I'm pretty sure everybody knows machine translation from just Google Translate, which is using neural approaches to machine translation. And machine translation, as you might see here, it's a challenging task. It's not easy. So how does let's call it traditional approach to machine translation or neural machine translation look like? Well, up until 2017, let's say, it was the encoder-decoder architecture. So there was one recurrent neural network that takes the input and generate some sort of dense representation. So this is called the encoder. And there is another recurrent network that takes this input representation and produces one token at a time, condition on the previous states and generates tokens. So this is the so-called decoder. And here we have a very standard abstract depiction of this architecture. So we have the encoder, which takes all these inputs, produces the dense representation here, and then it's going to generate the tokens. So this is a standard recurrent neural network encoder-decoder architecture for machine translation. So up to 2016, 2017, one of the state-of-the-art approaches. But what is the issue with these RNN architectures? Well, they are inherently segmental in nature. So if you run LSTM or gated recurrent units, so recurrent neural networks, you cannot parallelize. You have to wait, until each of these state is finished, and you cannot really parallelize these steps. It has also like big memory footprint because you have to remember all the sequence before moving on to the generation part. And if you model long-range dependencies, well, the distance plays a role because you might sometimes forget what you were talking here about, sort of. So these are some drawbacks, but empirically, RN architectures were really powerful for modeling that. But now we are talking about convolutional neural networks. So convolutional neural networks work differently and they are super easy to parallelize. So why not use convolutional neural networks for machine translation? And one property of convolutional neural networks is that, well, actually they look first on a local context for some features around each point. For example, in images, some edges and so on, like tiny patches. Or as we saw in the lecture on convolutional neural networks for NLP, they look for some n-gram features, or they extract from the embeddings of n-grams some important features for the task. But also you can stack the layers of CNN next to each other, and kind of you're extending the range or the receptive field of these convolutions, and they grow basically. And for example, here we have some local context, but if we stack another layer on top of that, then we're extending our receptive field. And by stacking next convolution layer, we're actually extending even more. So eventually, with very deep network, we're able to cover features or extract features from the entire input. And this is what I guess Jonas Gering and his colleagues from Facebook AI Research tried for machine translation back in 2017. So they took convolutional neural networks, and there were some preprocessing steps needed in order to work it out for machine translation. So input tokens were word embeddings. This is not surprise. And they took something which is called subwords. So we'll come back to that later on in this lecture. And the point is, as we saw before in CNNs, we need a fixed length input, but we take a maximum length of the input and just use the padding. So this is a standard thing. And now we think about it. So you have the words and you extract features and so on, but the positional information of the tokens is somehow lost. So for classification, it's fine because you want to extract features that actually influence the output, and no matter where they are. But if you do machine translation, well, the ordering actually matters quite a lot. So what I come up with is another embedding, which is the positional embedding. And what does it mean? So for each input position, there is another embedding. So apart from the word embeddings, there's another embedding vector. For example, for the first token, position 1, for position 2 up to position n. And these are initialized randomly, for example. So this is a random vector for token 1, token 2, and up to token n. And the word embeddings and the position embeddings are just sum up for each input token. And the advantage of this approach is that the model knows which part of the input output is actually dealing with. So it was an advantage to be able to dealing with this positional information in model. In fact, when they removed the positional embeddings, there was a drop in the performance, but only slightly. So positional embeddings was a thing that helped a little bit, but it wasn't the game changer. But it's an interesting concept, as we will see later. The cool thing about using CNNs for machine translation in this paper was that they were able to get state-of-the-art results, but these were up to 20 times faster than recurrent neural networks, than LSTMs on GPU. So if you have a model that is 20 times faster, it's a big deal, because you can train much more, much larger, much longer, and so on. So it's a really speed up. And given the performance is the same, this is like a superior architecture. Which means we could wrap the neural machine translation section now with sequence-to-sequence models, which are the standard approach, but have some drawbacks. And then we saw the convolutions and the concept of positional embeddings. We're moving on to the next subsection entitled "Attention is all you need." Why is this title here? Because it's a title of a paper that was one of the most influential papers in transformer models. Attention is all you need. So the problem here is how to model long-range dependencies in input. So for example, here we want to do named entity recognition. And we have tokens here told that Albert Einstein proved blah, 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 blah on seeing Einstein at B, and so on, so on. What we want to model here, for example, in doing entity recognition, is this that this Einstein here is the same Einstein here, or at least we have a mention of Albert Einstein, which could help us to better predict this Einstein as the entity, or maybe the same entity exactly. So for doing that, we already saw the recurrent neural networks or the stacking CNNs, but there is much more faster approach to modeling long-range dependencies, which is a self-attention. So we're gonna work out self-attention quite in detail to understand it in full. So let's say we have 5 tokens here in the input, the cat set, period, and there's a padding symbol. And here we might have some embedding representation. So for example, word embeddings. Right, so for word embeddings, we would represent each word with their hidden latent representation or embedding representation. So it's a vector. And we call this a matrix H. So this is a latent representation. What we're gonna do is to take this matrix H transposed. So we take this matrix H, transpose it, and just multiply. And we get a square matrix 5 times 5. So we have 5 tokens, so we get a 5 times 5. This is an example, of course. Typically it's much larger. So 5 times 5. These things are simply indices. So we have 1, 1, 1, 2, and so on, up to 5, 5, these positions. And what these items here in this matrix, what they mean is some sort of like raw association of each word with each word, or each token with each token. In the self-attention, we're gonna do one operation, and this is we scale each row by taking the absolute value and square root. So what does it make? Well, if you look at a square root, so if we take absolute value, we have only positive real numbers, and square root would be like something like this function, roughly. So the idea of scaling that is not to have super large numbers. In the next step, so again, we have this input tokens, 5 tokens, and through the operation we saw in the previous slide, we have this dot product of these raw associations matrix 5 times 5. Then we're going to apply a softmax per row. So we take each row, and these are some numbers in some basically non-negative real numbers, and we're gonna turn them into probability distribution, basically. So softmax is basically squashing everything first to the range of 0 to 1, and second, the softmax also makes sure that everything sums up to 1. So it's a probability distribution. So we would have like this as a histogram, for example, and we do it for each row. So then each row would correspond again still to one input word. So there is no change in the number of vectors here in this matrix, and each cell basically here shows us the strength of the association with each other token. So it's scaled or probabilistic view on the association strength between each two tokens from the input sentence. And in the next step, so this is the yellow matrix from the previous slide. This is after softmax. So we have a probability distribution on each row. And then we're going to multiply it with the embedding vector. So with the matrix H, which we had at the beginning after just the first layer after these input tokens. And what we're going to end up with is a self-attention matrix. And if you look at the details here, for example, so this would be a first row multiplied by first column here, which would give us the first item. What is this here? What is this saying? So we have these are some embeddings, so some real numbers, but we're gonna multiply that by this probability distribution. So if I just plug it here as a probability distribution, like that, a histogram, it's gonna weight each of these elements in this first dimension of these embedding vectors. It's gonna weight it and sum it up. So here we get a sum of strength of association from each of the other words, and that is for each of these dimensions. So this is the first dimension, then second dimension, and so on. So we really get some contextual information from all the other tokens, which are somehow probabilistically weighted. And here's the last step, so stay with me. We get this self-attention from the last step, and there's another method utilized there, which is basically taking the self-attention and sum up with the matrix H, with the embeddings matrix, and we call that residual connections. So we get this self-attention, which already has some strength or associations between all the words, and these are uncontextualized embeddings, and we just sum them up together to get residual connections. And as this paper said, attention is all you need. Well, we just described the self-attention, but we don't need only one. We actually have n attention heads. So the block we were describing in a couple of previous slides, we run them in parallel, concatenate, and then stack them on top of each other m times. So we're gonna get a very big architecture that utilizes all these operations and self-attention. And why the self-attention could be working well, and basically I highly recommend to read this paper, Attention is All You Need. It's about machine translation. So they were using this attention mechanism for machine translation. And what they show is that, well, the self-attention layer, it really connects all positions with a constant number of sequentially executed operations. So there is ON, so the complexity is bounded by the linear complexity, because we have n sequential operations. So this is like in recurrent layers, but we have the sequential operations. But here in self-attention, we have matrix multiplications all the way around, and we just, for computing the attention, Computing attention just scales. It's a two matrix multiplication, which means it just grows. You grow your memory footprint, for example, because you need like n square memory for storing the matrices and so on. But it's just super fast. So there is no difference between multiplying 5 times 5 versus 10 times 10. While in recurrent, you need that many operations in sequence. So self-attention are fast. Which brings us to check this attention part, and we know that attention is very efficient for long-range dependencies. So the show must go on. Where's BERT? No, stay with me. We're getting closer. So out of vocabulary words. Why is it important? Well, we'll see it plays a very, very important role. If we are in machine translation, we're working with fixed vocabularies. So we collect some vocabulary in both languages, and this is what we work with. But even though like translation is fundamentally an open vocabulary problem, that's the issue. So we have names, numbers, dates, and some of them you can encode or anticipate and put it into vocabulary, but some of them you will never see until the test time, where your system will just fail and it will say, well, the most frequent words are used. So you collect your vocabulary up to, let's say, 100,000 words, 200,000 words. And then the other is just some unknown token, which could work, but it's not always wanted. Typically, one approach used to be taking for out of vocabulary words, you would, if you encounter a word which is not in your vocabulary by machine translation, you just copy one-to-one from source to target. You just take the word which is in the source, you cannot translate it, so you just copy paste it. It could work for names and numbers, but it doesn't give you like very precise translation. So this is what motivated subword units. And I believe one of the first using subword units for in NLP, well, actually they use it for in speech recognition or in voice search in Japanese and Korean. It was in 2012, Schuster and Nakaima. And the issue they had with Japanese and Korean was that the vocabularies were just too large for these two languages, were extremely large, and they would just produce so many out of vocabularies. So the translation or not the translation, but search by voice would be basically impossible, or to reconstruct the full words, full vocabulary was not doable. So they took the subwords, which I'll explain in the next slide, but later it's known nowadays as a word piece model, and it was adopted by neural machine translation at Google and later on by the BERT model. So this is why we're talking about it. And why should subword units give better translation than just copying from back of dictionary? Well, the argument was that open vocabulary machine translation is better by representing a rare and unseen word as a sequence of subword units. So it's better to have a sequence of subword units and represent some words that are very rare, don't occur that often, and it's better than just simply copy pasting the input to the output empirically. But now what these subword units are. So similar to vocabulary, it's a list or a set of all known subwords, including characters, which means that each word is either, so word as we know, a lemma from vocabulary is either entirely a word piece unit or can be split into several word piece units. And here's an example. The Declaration of Human Rights, the first sentence, which is now split into the word piece model, which is shipped along the word. So if I take the sentence, all human beings are born free and equal in dignity and rights. So it splits into tokens. All human beings are born free and equal in dignity and rights. So, well, this is just a simple tokenization. So where's the catch here? So we'll see the catch in the next slide. Because word piece units came from machine translation or multilingual search in voice. we can try to tokenize other languages. So we have alle Menschen sind frei und gleich und Würde und so weiter. And here we see that, well, oh, okay, we're splitting the first word, alle, into 2 tokens. So these 2 hashtags is a special symbol that we split the previous word. Because alle is not a unit in this word piece inventory. So we're splitting into something we know, which is all. And then the suffix e, alle. Menschen is the same thing, so a Menschen. And now you might be wondering, well, okay, that's actually pretty clever, because German and English are somehow close to each other, and if I split all and men into alle Menschen into all something and men something, I'm getting something which is pretty close to the English meaning. So there is some benefit of having these subword units for machine translation. So it goes on and on and on. So you might work out the example here. As we saw, it's lowercasing and it's removing the punctuation. But how more languages? So here's 3 other languages, which the first one, I guess it's Russian. The second one is Czech. And the third one, it's Georgian. And Georgia has a very beautiful alphabet. It's a very beautiful language. Unfortunately, I can't read it. I can neither read Azbuka here. I could read a Czech one, but doesn't matter. What do we see here? It's again splitting, but now we see like we have fewer word piece units for these languages. So it's splitting quite a lot here into sub pieces, which has a reason because of the training, which we'll cover later on. Also, we see for the Georgian language here that it actually produces some unknown subword units, because it doesn't actually know all of them. So it represents some prior probabilities of these things in the training corpus, or actually how these word piece units were trained, or on which data sets they were trained on. So it could be even with word piece units. There could be alphabets that are just not covered there in this particular instance of trained word piece units. So how Schuster and Nakayama trained the word piece inventory? It's an iterative process. So first you take all characters in all the alphabets you have. Then for each possible tuple of these word piece units in your inventory so far, create a new candidate word piece units, and then build the language model and compute the likelihood on the corpus. And then select the candidate with the maximum likelihood and add it to your word piece inventory. And then go back to second and generate another candidate or candidates, then multiply likelihood and so on. So it's, it sounds really brute force, but with a couple of heuristic tricks, it could be super fast and train within a day or 2 with very good word piece units. So I believe now you understand how these word piece units can solve the problem of out of vocabulary words and how they are truly multilingual. So the next part deals with something which we haven't talked about yet, I guess, but it's a very important concept in deep learning in general, and this is multitask learning. And it's quite an old concept, so it goes back, well, many things in deep learning are quite old, but this one plays an important role nowadays, and it dates back to the 90s. This is one of the papers. Multitask learning. And what does it mean? That we can learn several tasks in parallel, and we can use a shared representation. So for example, here we have some input. These could be our words or features or whatever you have, and we have some connected architecture. And then we have 5 or 4. We have 4 different tasks here. And this could be, name and recognition, and this could be sentiment classification and so on. It doesn't make sense in this architecture, but just, you have some ideas. Well, different tasks, and we can train them one after each other or in parallel while using some sort of shared representation in the middle. And the idea is that we help with inductive transfer. So we'll learn something that each task can benefit from, and each backpropagation then, again retrains these shared representations. So we learn something which is more general, and it should help each of these tasks. And one early example of multitask learning in NLP could be from Andreas Sogard and Yoav Goldberg in their ACL 16 short paper. They tried several intermediate tasks. So for example, here's the input and data for the main task, and the network goes like that. And then there's one task which is, for example, part of speech tagging. And this is one task you train your network on, and there's another one which is the so-called the main task, and it could be, for example, super tagging or syntactic chugging. So these are some still low level but higher level than part of speech tagging. And you would basically train these two objectives at once and train a network, and these layers here would be shared for both of these tasks. And what the authors say that they suspect that if there is a hierarchy between the different tasks, so for example here part of speech is considered more low level than syntactic chunking or super tagging, we show that it's worthwhile to incorporate this knowledge in the multitask learning architecture design by making lower levels tasks affect the lower levels of the representation. So they show it in this kind of linguistic learning that multitask learning could be beneficial. It's not always like that, and it's always hard to find what could be these different tasks and what the architecture should benefit from. But as a concept, it's well known, and it's somehow understood and might be very beneficial. You can also train your task train your network on a different task, in fact. And this is another paper from, I guess, Facebook research called Infercent 2018. And what they did is they took this Stanford natural language inference corpus. So we talked about it in the beginning of this lecture. So this entitlement, contradiction, and neutral. And they trained a network on this NLI. So the architecture that they used was some recurrent network LSTM or gated recurrent unit. So basically it learns a representation in the last hidden state. And they use this representation then for training on another task. So they took this representation and then train other task, which is Microsoft Research paraphrase corpus. And the task is to detect paraphrases. So it's very different from natural language inference, or even with combination with images. So COCO dataset is for caption image retrieval, where you have an image and a couple of captions, and you want to find out which caption of the image is the most appropriate. And they show that models learn on this lexical or semantic inference task actually perform better when pre-training model on these perform better than models trained in some unsupervised conditions. So there were other approaches before this Infercent paper that try to learn some representation in an unsupervised, something like word-to-vec, but on sentences. And they show training on some meaningful task like inference is actually helpful for the other tasks. So they transfer the learned representation. Which finishes our short recap of multitask learning. And we know that shared representation improves generalization, and then we can use transfer learning to learn on one task and fine-tune or co-learn on another task. So I guess this is the last one on the roadmap before actually jumping on BERT. And this is the unsupervised pre-training. It's going to be pretty short because we know most of that already. So unsupervised pre-training, what is unsupervised in deep learning? Basically, well, not because deep neural nets, as we know them, there could be other architectures that actually are unsupervised using some probabilistic graphical models. But the networks we've been working with so far are actually trained with full supervision. So you have some XY pairs, and you train on them. And even autoencoders are supervised by the reconstruction error. So autoencoder is something which takes an input, learns some hidden representation, which is typically small, and then tries to reconstruct the input again and just compares to each other how well it mimics or reconstruct the input. So it's again supervised because we have some signal here. So we would have here XX as the training pair. So the unsupervised training scenario usually means that I don't have any labeled data, but I can design some proxy supervised task. So for example, given a context of a missing word, predict that word, which we know from BERT embeddings, and then create a positive and negative instances by taking a large unlabeled corpus, and I can swap words and so on. So this is what we know from word2vec. Word2vec is we consider it unsupervised because we don't have any labeled data, but in the way of training, it's supervised because we're creating the supervised task by taking things and turning them into prediction task, which concludes the unsupervised pre-training on the roadmap. So it's a long trip so far, right? So all of this is important to understand before we actually jump to the BERT model. And now BERT will be a piece of cake for us to understand. So very abstract view on BERT. What is it? We have some input text, so it's a lorem ipsum dollar and so on, which is tokenized. Then there is BERT, so some architecture, and it learns a contextual representation of each token. So each token, as we have here, will be given a contextual representation. And then we have some task which we want to do, for example, natural language inference, sentiment analysis, part of speech tagging, and so on. And we want to solve this task. So the first design choice in BERT is the tokenization. And we're tokenizing for a good reason. We're tokenizing into multilingual word pieces. So this is what we already saw which comes from machine translation. So we have a word piece inventory, and these are subword units. BERT is using 30,000 word piece units, but there are the original BERT, but there are some newer models that are actually trained on 100 languages, and the word piece inventory is much larger, so over 100 units. What are the implications of that for BERT? Is that BERT can kind of consume any language, because now we don't have the problem of out of vocabulary words, because everything is a word piece inventory, and given it's large enough, 30,000 or 100,000, any input any meaningful input in any language is possible. And we have the word piece embedding. So each word piece token from the input is represented by a word piece embedding. So it's the same as word embeddings, but just not attached to a word, but a word piece, so subword unit. And typically they are randomly initialized or could be pre-trained, doesn't really matter now. Then what we also remember from the convolutional neural networks for machine translation, we have each position input associated with the positional embedding. So again, we have word embeddings and positional embedding. So this could be position 1 embedding, position 2, and so on. We have to limit the length. So we limit the length of the input to 512 word piece tokens. And how are we going to do that? So we use padding. So we have lorem ipsum and pad up to 512. So each sentence or each input sequence is maximum 512 word piece tokens long. There's other specialties in BERT, and that is we append the first token, which is always a special token called CLS. Why is that so? Will be clear in the next slides. If we have a task that involves two sentences, for example, the natural language inference, so we have the text and hypothesis. So for example, there's a man standing and a man is playing football. we split, or we put a delimiter between these two sentences, which is the special token separator. And we have also special 2 segment position embeddings, and I'll show later on what this means and why is it important, which is now the case on this example. So let's say we have this input. My dog is cute. He likes playing. So 2 sentences. We have this special token CLS as the first. Then, since this is involving 2 sentences, we put a special token separator. We put a separator at the end as well, and there could be padding because this is very short. These are our input. So we have, these are word piece units or word piece tokens, as you can see here. So playing was split by word piece tokenizer into play and ink. So these are, this is split into 2. So we have these token embeddings. Then we have the position embeddings. So this is just simply position 0, 1 up to 512. And then we have this special segment embedding. We have only 2 of them. So each token is associated either with segment embedding A or segment embedding B, which means this comes first and this comes second after the separator. So this is it. Which means now we understand how the input of BERT looks like. So we have these BERT pieces and we have some special embeddings. What comes now? The next piece of this architecture of BERT is something we know already pretty well, and this is the good old friend self-attention. So from the attention is all you need paper. So basically this is one part of that. And as we saw, so this is again the depiction of the attention, but I'm not going to go into the details now because we know it already from the previous slides. But we have these heads, so these are in parallel attention heads, and there's 16 of them, so quite a big. We have this residual connection, so we just use attention and add the latent matrix. We have layer normalization, and we stack these things up to each other 24 times. So it's a huge network, which has very many trainable parameters. It's a very big thing. But well, technically there's no surprise. So we've seen it already. It's basically BERT is taking the attention is all you need transformer and just make it very big and very deep. Which means we know how to take the input, we know how BERT is working, and now we actually know that how these contextual representations are learned because they are taken from the self-attention. And now we have to have a look how these tasks are looking like. How can BERT model the downstream tasks? And now we will understand why the special CLS token is there. What does it mean? So no surprise, CLS is for classification. And here, this is how BERT is modeling sentence per classification task. So, for example, natural language inference, and so on. So we have first sentence, and now, well, actually perspectives on BERT or the architecture are changing. So sometimes we have it from left to right, sometimes from bottom to top, sometimes top down. We talk about the depth of the network, but it goes up and so on. So it might be confusing, but now we have the tokens here at the bottom. So we have the first sentence, then we have a separator, then the second sentence. For each of these tokens, of course, we're learning the contextualized embedding here in the end. And for the CLS token, we're learning also some contextualized embedding. And we're gonna use this embedding here as the input for the prediction of the class. So then we run some softmax on top of that. And we just, this will be our feature representation of the entire, of both of these sentences, basically. It's gonna be propagated through the network up until here to this embedding. and we're gonna use softmax for classifying 2 sentences, which is the same thing for single sentence tasks. So for example, sentiment classification. So now we don't have the separator here, we just have 1 sentence, and again, it's gonna be propagated through all the network up until here, which will be used as a class label, or basically we're put a softmax or sigmoid, whatever, depending on how many classes we have on top of that, and we're just train the downstream task. The BERT model also can model, the BERT model models sequence tagging tasks, so classification for each token. And for example, name entity recognition. So as you remember, name entity recognition assigns to each token a particular label, which is using the BIO tagging. So beginning, input, and out. So for example, here would be out token, beginning the person, and so on, so on, so on. And how does it work? So again, we have these tokens and their representation up here or down here. And we take the embedding of that and put again some classifier on that, such as softmax, and classify each token into the particular class. In name entity recognition, we have several dozens of classes, for example. And the point here also is that we don't condition this output. So for example, B-pair, we don't condition on the surrounding predictions. So if you're familiar with conditional random fields, conditional random fields, it's also quite a popular framework. So it's probabilistic graphical model for tagging, sequence classification, and there you would condition on each of the surroundings. So this would be our tokens, then these would be our predictions, and here is undirected edges between these random variables. So basically you would do like a joint optimization of all these together. But this is not what BERT is doing. BERT is basically taking the embedding of each particular token and just run a classifier on that. And it works better than conditional random fields. So again, we covered input, we covered the transformer, the embeddings. Now we know how to represent several tasks at once. And now you might be asking, wait, so this is it? So we just how can we use it? How can I use it? And of course, we have to pre-train this thing. So this is the funny part. So pre-training. And this is where the fun starts. So BERT was pre-trained on using multitask fission. So there are 2 tasks, and it's unsupervised in a way, as we just were talking about, unsupervised in a way we don't use any labeled data. So we don't need any NLI as in InferSend. So InferSend needed NLI for pre-training. Now we don't need any labeled data. We can run it on unlabeled data, and it could be really, anything and super big. So we prepared 2 auxiliary tasks that need no labeled data. This is the big advantage. And what we're gonna do is to prepare 2 tasks. One is the so-called close test task. So we want our network to predict a masked word piece units. So here, if I go to this architecture of BERT, we randomly take a token and just mask it, make it a gap. And we want the network here to output the prediction of this token. So we have like 30K classes. If we have 30,000 word pieces, this is 30K classification. So we want to predict the missing token here, or missing word piece unit. The second task is quite interesting. Why is that so? So maybe you want to give it some thought afterwards. And it's predicting whether the second text segment appeared after this first segment. So we have 2 sentences, or better, segments. These are not really sentences, but it's just for simplicity here, sentences. We have sentence 1 and sentence 2. We take these two from some corpus, and in some cases we keep them as they were. So first sentence 1, then sentence 2. But in some cases we just swap them, and we want this representation to predict whether the second was after or before. So this is somehow for learning some coherence in the text, and maybe for some logical coherence or logical properties, or learning something about relationships between sentences. So where did the original BERT authors took the data? They took the entire Wikipedia corpus in 100 languages, so 2.5 billion words, quite a big thing. And to generate a single training instance so we need to train instances for generate instances for training deep learning models. They sampled 2 segments, and for the second task, they replaced this second segment randomly. So they didn't swap them; they just replaced the second segment by some other random stuff. And for the close test task, for task 1, they choose random 15%, some fraction of the tokens, and in 80 cases they replace that with a gap, with a mask thing. So some subsampling was there, not all tokens, not all the time, but some small fraction of that was replaced with the mask. Here's an example how this input would look like. So for the first task, we would have the man went to something store. He bought a gallon something milk. So I guess it would be the man went to the store. He bought a gallon of milk, and the label is next. So this second segment, so this is segment 1 and segment 2, and most likely these two were occurring in the text as they are. So if we had an input text, we would have segment 1 and then segment 2. So this logically makes sense. And then another input, the man, now masking another word, went to the store. Penguins are flightless birds. Yeah, so as we see, this is like if this were segment 1 and that would be segment 2, we would have in the input text segment 1 and then somewhere randomly segment 2 from completely different Wikipedia page, for example. So there is no logical relation in these two. So this is how the generating the pre-training data for BERT would look like. This is simplified example because we don't have padding here. The actual segments are longer and not necessarily actual sentences, just spans. So this is now a beautiful short English sentences to make the point, but in reality we just sample some texts. And here the word piece units are matching full words, but recall that we have some other languages that weren't that nice in segmenting the text. And this brings us almost to the end, because now we know how to represent text. We know there's this transformer architecture. We know how to learn contextualized embeddings. We know how to fine-tune it, or actually how to represent our tasks. We know how to pre-train this thing. In the original BERT paper, it was quite expensive. Well, depends. 4 days on 64 TPUs. So, well, it's a big thing. I guess 500 is just way too little. It must have been much more. Anyway, depends. Costs are changing and GPUs are available, and I guess you could be able to train BERT nowadays on much cheaper. But there are bigger models that you might want to train. And the point is, once this thing is pre-trained, you can just transfer and fine-tune on your task. So you just trained on, for example, on sentiment analysis, and you just run on your small corpus, small data task, and you would get state-of-the-art results. state-of-the-art results was the case when BERT came out in 2018, 2019, and on many NLP tasks it was the case. Of course, nowadays, there's new challenges, and BERT is considered mainstream, so which is quite funny. It's just two years almost, or 2.5 years, and something which was super game changer is now considered baseline. Quite interesting. But I hope it gives a good overview, like what was necessary to understand BERT, or what was even before BERT, which ideas were combined together, and if you knew all of these, maybe you would just came up with BERT as well. But I'm afraid there was a lot of trial and error as well. So why exactly using this CLS token? Why exactly the separation token, and so on? So BERT actually stays on the shoulders of many clever concepts and techniques, but they mastered all of them into a single model. So they really took it and mastered that. And why is BERT really important, and why is that such a great concept? Is that you can run it on many tasks. It solves many tasks at once. So if you imagine you would have a sentiment classifier and then something for name and recognition, you would need basically 2 models. But now you can use pre-trained BERT model and fine-tune it on one task and it will work, and then fine-tune it on another task and it will work too, and give really superb results. So this is super clever. What we can't tackle today, because it's already a long lecture, I'm afraid, is why the heck is that working, or what does it do, and why does it work so well? And for tackling that, I really suggest to have a look in this Tackle paper by Anna Rogers and her colleagues that appeared in Tackle, called The Primer in BERTology, What We Know About How BERT Works. So it's a kind of state-of-the-art summary of what we believe BERT works as it works, because it's hard to explain models that have 500 million parameters. How can you do that? Not by hand. So there's clever techniques to look into detail and have some insights into that. So I highly recommend to have a look at this paper. Which brings me to the end of this lecture. So I hope you enjoy that. You enjoy the path by exploring BERT. There were no costumes. I'm sorry about it. Maybe next time. And if you have any questions or comments, just drop it here on the comments, or use Discord or Moodle. And I hope to see you in the next lecture. Thanks a lot.